When you look at a huge skyscraper or a massive bridge, you probably just see concrete as, well, gray, solid rock, right? But what if I told you that inside every single one of those mixer trucks is a super high-stakes chemistry experiment? We're talking a delicate balance where just one wrong ingredient, this kind of chemical super potion, can be the difference between a rock-solid building and a multi-million-dollar disaster that just refuses to set for weeks.
All right, so here's what we're going to get into. First, we'll look at the big problem with modern concrete. Then we'll meet this amazing chemical super potion that's supposed to solve it. And this is the interesting part. We'll see why picking that potion just based on price can be a huge mistake. We're also going to investigate what happens when good concrete goes bad, witness a literal clash of molecules, and finally, check out how the pros test for the perfect mix so they can avoid a total catastrophe.
Okay, so here's the fundamental challenge, right? Modern buildings, they're not simple boxes anymore. They're full of these crazy complex shapes, and they're packed with steel rebar. Now you have to pour concrete, which is basically liquid rock, into all these super tight spaces, and it has to flow perfectly, almost like honey, filling every single little nook and cranny. No gaps allowed.
Now, the easy answer seems obvious, right? Just add more water. That'll make it flow better. But that is a total trap. See, every extra drop of water you add creates these tiny little pores in the concrete once it hardens, and that makes it way, way weaker. So the engineers are kind of stuck. They need that flow, but they absolutely cannot sacrifice strength. So how do you solve this puzzle?
So what do the pros do? Well, instead of reaching for the water hose, they turn to chemistry. They add just a tiny amount of a very special ingredient. Yeah, you can totally think of it as that super potion we mentioned, something that just unlocks concrete's hidden potential. This stuff is called a superplasticizer. It's basically a water-soluble polymer that works on a microscopic level. It's pretty cool, actually. It wraps around the individual cement particles and gives them all a negative charge. And what happens when you have a bunch of things with the same charge? They repel each other. This electrostatic repulsion just blows apart all the clumps and lets the whole mixture flow incredibly well. And the best part? You do all this without adding a single extra drop of water.
Okay, but here's the thing. Not all of these super potions are created equal. Not at all. There are a few main chemical families. You've got the older ones like lignosulfonates and sulfonated naphthalene formaldehyde. Let's just call that SNF. It's easier. Then you have the newest, most powerful generation, which is called polycarboxylic ether, or PCE. And the choice between these, that's where our story starts to get really, really interesting.
Imagine you're the project manager. You're always thinking about the budget, the bottom line. So you look at the price tags for these different chemicals, and the decision seems, well, pretty straightforward, doesn't it? But that initial cost, it can be so misleading. If you just look at the cost per kilogram, the high-tech PCE stuff can look wildly expensive. We're talking more than double the cost of the common SNF-based ones. Any accountant would look at that and immediately point to the cheaper option. But that's before you factor in performance.
See, the whole picture changes when you look at how effective they are. These new PCEs are so incredibly efficient that you need way less of them to get the exact same result. So let's say a kilo of PCE has a relative cost of like 100, but you only need a tiny, tiny dosage. The SNF is cheaper, sure, maybe a relative cost of 40, but you need to use double the amount. So when you actually do the math, multiply the cost by the dosage to get the true cost in the final mix, the numbers get surprisingly close. Actually, when you run the numbers for a real-world mix, the actual cost difference between the so-called expensive high-tech option and the cheaper one can be as little as 25%. All of a sudden, that huge price gap, it's pretty much vanished.
And this is the crucial point, right? That initial price tag is totally deceptive. You're not just buying a chemical in a drum, you're buying a certain level of performance. And a lot of the time, the most efficient chemical actually gives you the best value, even if its sticker price is higher.
But hold on. Even after you do all that smart math, you are not out of the woods, not even close. Because sometimes, even the right admixture can react with the wrong cement, and the result is total failure. The puzzle just got a whole lot more complicated.
And the consequences? They're terrifying. I mean, listen to this. This is a direct quote from a researcher talking about reports from actual job sites. Imagine pouring the foundation for a skyscraper and having the concrete still be mush 2 weeks later. That is a real-world nightmare, and it's caused by something called incompatibility.
This chemical mismatch, it can show up in a bunch of disastrous ways. The concrete could suddenly lose all its flow and just become totally unworkable, or it might refuse to harden for days.
And days. You could see the water and the rocks start to separate out. Or, maybe worst of all, it just might not get as strong as it's supposed to be, which compromises the entire structure.
So what is going on here at the molecular level? To really get what's failing, we need to zoom way in and witness a pretty dramatic clash happening between two key molecules in this whole mix.
So what's the deal? What is causing all this chemical chaos? Well, the answer is actually pretty simple. It's a case of magnetic attraction gone horribly, horribly wrong. Okay, so our first character in this little drama is a compound in the cement called tricalcium aluminate. Let's just call it C3A. Now, when the cement is being made, these C3A particles, they tend to pick up a strong positive charge. Just remember that. C3A is positive. And our second character? That's the SNF superplasticizer we were talking about. Its whole job relies on its long molecules having a strong negative charge. They're supposed to give that negative charge to the cement particles, so they all push away from each other. And here's the conflict. As soon as you add that negatively charged SNF to the mix, those positively charged C3A particles act like tiny, powerful magnets. They just aggressively grab onto the SNF molecules, basically hijacking them before they ever get a chance to go do their real job. The super potion gets neutralized before it can even get started. And this leads to a really bizarre paradox. This one single reaction causes two problems that sound like they should be complete opposites. First, since the SNF is hijacked, it can't disperse the cement, right? So the concrete loses its flow really fast. But at the same time, the C3A particles are now all coated in this SNF, which blocks them from doing their normal job, which is reacting with gypsum to kick off the hardening process. So get this, the concrete won't flow, and it won't set. It's the worst of both worlds.
So with stakes this high, how on earth do engineers make sure this kind of chemical clash doesn't happen on a massive project? Well, they definitely don't guess. They test. And the method they use is surprisingly simple, almost elegant.
They use this little tool called a marsh cone. It's basically just a standardized funnel. It's simple. You mix up a small batch of cement paste with the exact superplasticizer you plan to use. You pour it into the cone, you open up the little hole at the bottom, and you just time how long it takes for a certain amount to flow out. The faster it flows, the better the workability. And by running this simple test with a few different amounts, you can pinpoint the exact moment you hit the point of diminishing returns. They call it the saturation dosage. That's the sweet spot. It's where you've added just enough of the super potion to coat all the particles, and adding any more just won't do anything. It's the key to finding the most efficient, most compatible mix before you go and order 100 truckloads of the stuff.
So, this brings us all the way back to where we started. The next time you see a concrete building, you'll know what's really going on. It's not just some simple material. It's the end result of a carefully controlled, super high-stakes chemistry experiment. And understanding that invisible clash of molecules, well, that's the real key to building the entire world around us.